Your talk today will be Emergency Engineering, Translating Innovation into Impact. Welcome, Andrew, Professor Armani.
So thank you very much for that fabulous introduction. I'm going to obviously share my slides, but get the laser pointer. Okay, there we go. And I changed the title because I noticed my title was the exact same title that Alice used, so I didn't want to have the same title that Alice used. So I changed it at the last minute, in other words, this morning. So Paul, I didn't have a chance to tell Paul. I didn't want to put more things on his plate.
No problem.
Again, thank you very much, Alice, for inviting me and being an amazing organizer of this entire series. I know it's a lot of work to organize one seminar. I can't imagine organizing, a seminar series a week for months during the middle of a pandemic. And thank you, Paul, for stepping in last minute today so Alice can take a much needed vacation. I'm sorry, even though we're, down the street from each other, we're sitting alone in our homes at 6 a.m. So the first thing I always want to do is thank all my group members, my research team. They're the ones that actually do all of the research. So even though, I get to present it, they're the ones that are in the lab. Specifically today, I'm talking about the work by Lexi Schultz, Renee Zito, Dongyu Chen, as well as two group alums, Samantha McBurney and Alexa Hudnut. And then also several of our collaborators, SMP Engineering, Rosemary Shea at Keck Medicine of USC, and Joseph Kirchvik at Caltech. So our group, as Paul mentioned, has a lot of different areas that kind of come together synergistically to address two main themes. But in general, we work on combining new types and developing new types of nanomaterials, both organic small molecules and inorganic nanomaterials like zinc oxide nanostructures and quantum dots, to make new types of integrated optical devices like lasers and frequency combs, to try to address challenges in portable diagnostics as well as disinfection. So we work kind of through all different length scales as well as all different complexities in terms of system integration. And again, we try to address integrated photonics challenges, which have applications in lasers and nonlinear optics and cryptography, which means a lot of our materials are nonlinear materials. So for example, several photons will come in and get converted to a single photon, but convert energy. Optical energy. And then we also work in healthcare. So trying to understand disease progression, do disease diagnostics, as well as develop new ways to actually deliver therapeutics. And today I'm going to focus on that healthcare and wellness theme. But if you're interested in a different area and you came today to ask a question about one of the other areas, you can do that. I have backup slides.
Your sound is cut out, I'm afraid. We heard right up until I have backup slides. Try again.
Is it back?
Better. It's back.
It's back. Okay, good. Okay, so today I'm going to talk about UVC disinfection, specifically the background and mechanism of UVC disinfection, as well as some of our recent work. And then as well as using light to try to understand and develop new diagnostic methods, specifically a malaria screening method and a tissue analysis method. So taking a step back, our healthcare ecosystem under normal operation consists of a hospital and community setting that requires many different components in order to be stable and operating in a robust manner. So it requires instrumentation and diagnostics, personal protective equipment, disinfection technologies, personnel. So all of these different components come together synergistically to support our healthcare workers and patients as well. And normally, all of these different needs can be supplied by companies, industry, manufacturers, and so it forms this very nice, robust ecosystem. The challenge is that when the hospitals suddenly have a surge in patient demand, this ecosystem becomes destabilized. So you can think of it like a chemistry equation, right? When suddenly you have an increase in demand on one side, that reaction can become completely destabilized. And this is what's happening, right now. We're in the middle of a pandemic. The hospital needs are increasing, and the ability of companies and industry to keep up with that demand is basically not possible. And this is what caused the need for PPE reuse. And in order to reuse PPE, there was an increase in demand for disinfection technologies. And so to address that increase in demand for disinfection technologies, the engineering community stepped in to try to develop a whole host of different approaches. So some of them included things like vapor phase alcohol methods to try to reuse N95 masks and KN95 masks. Some of them included walk-in UVC methods. But this idea of trying to reuse PPE required the development of new disinfection techniques, most importantly, disinfection techniques that didn't necessarily rely on companies or industry to actually develop them. So they could be built by the engineering community. So universities, researchers, this group of people called citizen scientists. So people at home. So when you think about developing a disinfection method, you first have to consider, what are you trying to disinfect, right? Like, what are you actually trying to clean and remove? And what type of approaches can you use to do that? So when you're trying to disinfect, there are two big picture approaches. So you can think about disrupting the viral replication or disrupting the virus structure, which in turn will disrupt viral replication. So as an engineer, these are kind of the big picture concepts. So the key features for viral function are things like the spike protein, the envelope protein, and the RNA. And obviously there are many more complex mechanisms, but these are kind of the big picture when you're thinking about a disinfection approach. And there are three main categories that are used in terms of physical mechanism. The first is thermal, which includes things like high temperature ovens, which can be either wet or dry. The advantage of using a very humid environment is that a humid environment will destabilize both that envelope protein, whereas the heat destabilizes that spike protein. So then it's a twofold mechanism, so you get a much more effective disinfection treatment method. Then you have chemical, and this includes things like bleach, hydrogen peroxide, alcohols, various types of alcohols. And chemical methods destabilize, again, both that envelope protein as well as the S protein. So again, you're targeting two different aspects of the virus, so it's a very effective method. And then the third category is irradiation. And irradiation can include things like X-rays, microwaves, as well as UVC. Depending on which irradiation method you're using, it can destabilize different things about the virus, but UVC specifically targets the RNA. Microwaves, for example, actually are a thermal method, so microwaves thermally heat the virus, so therefore it becomes an S protein mechanism. So it's indirectly a thermal mechanism, even though it's not directly applying heat. So it's kind of an interesting approach. Anyway, so we're going to talk about UVC. So as a refresher, in case you've forgotten DNA and RNA, which many of my undergrads, the last time they took biology was, freshman year in high school. So DNA and RNA are comprised of two different categories of molecules, purines and pyrimidines. So these types of molecules bind with each other. So guanine binds to cytosine, and adenine binds to either thymine if we're talking about DNA, or uracil if we're talking about RNA, and these are kind of general big picture statements. DNA in general is a double helix. RNA in general is a single strand. So therefore, if you develop a technique that affects the pyrimidine groups, it will disinfect both bacteria and RNA. So it's a fairly straightforward philosophy for trying to disinfect and create a universal disinfectant method. So how does UVC work? So if you think back to that DNA and RNA, usually you want to have your ATs bind to your GCs, but if you can make your, thymines bind to your thymines, then suddenly you're breaking up that base pairing structure. And if your base pairing structure is no longer functional, then your DNA is no longer functional and you can no longer replicate your bacteria or replicate your RNA. And that's exactly what happens when UVC interacts with your DNA and RNA. So instead of having your thymine bind to its normal mate, adenine, thymine binds with thymine. And so you end up with something called dimerization. And because you have dimerization, suddenly your backbone becomes self-binding as opposed to binding across and binding to its natural mate. So before UVC exposure, you have this very nice lattice or ladder structure. And after, you end up with kinks. And because of that kinking structure, things like transcription, which is when it replicates, no longer happens, and therefore your virus can no longer replicate itself, and therefore it's basically dead. Its lifespan is decreased. So UVC originally found its home and its primary use in things like water purification, air purification, and those are still the dominant markets for UVC. More recently, it actually started being used in healthcare. So even though the most popular knowledge of UVC, especially currently, is as a healthcare application, it's actually used most commonly, and the largest market is in pollution and water treatment facilities. But in the healthcare application, it's used for conventional like handheld devices, and this looks almost like a toaster oven or microwave type system. So it has like a small front lid. You put your device in, close it, put it in there for about 3 minutes, and then pull it out and your handheld device is cleaned. Then it's also used in biology labs. So biosafety cabinets often have a UVC treatment. So after you do a cell culture, you take your cells out, you then flip on a little light, and you can do a UVC treatment. And then more recently, robotic systems have been developed. So these usually have an automated mobile base that can either simply be used as like a push cart, so you can wheel them into a room, or they can be semi-autonomous and kind of roam around a space without needing manual intervention. And the UVC lights are mounted vertically, and they're very loud. Or, Paul, if you're holding something up, I can't see it. Just want to toss that out there. Okay, so there are two different kind of strategies when you're integrating PPE into a hospital system. The first is to have a primary PPE site within a hospital, and the second is in a situation like today. So the first approach is you have a primary point, and then you have all of the different healthcare sites linked to that primary point. And the additional sites could be things like the emergency room, the intensive care unit, maybe a general care facility, patient rooms. And this type of structure allows for that primary disinfection site to include thermal, chemical, as well as irradiation methods. And it creates a very robust sterilization point within a healthcare facility with very good infrastructure. However, when healthcare facilities become strained and overcrowded, they have to begin thinking about alternative structures. And an alternative structure, so a distributed disinfection network, has to be created. And distributed networks, you can think of this almost like network theory. A distributed network, you still have that primary network point, but now to increase the number of locations for patients to be located, you have offsite networks for PPE. And these secondary networks may not have the same number of resources as that primary network, but it does allow for an increased number of patient sites. So now a healthcare facility can have and host more patients, even though the ability to sterilize their equipment is lower. And a real world example of this is happening now. And it is in places all over the world. So these are just a few examples that I found, but pretty much every continent has delocalized disinfection networks. I'm sure I could have found hundreds more pictures. But basically, delocalized healthcare centers are being launched in football stadiums, in convention centers, in parks, and obviously all of these delocalized locations need delocalized disinfection sites. So in March, the Keck Medicine Center of USC, which is the USC hospital, put out a call asking for all the available PPE, which I think almost every hospital in the US did that. And I emailed back and I asked the CEO what else they needed. And that was their immediate call, was they needed other ways to disinfect their PPE. And they gave us a list of criteria. And this was literally their list of criteria. So they wanted something that could achieve 100 millijoule per centimeter squared of UVC intensity. And that number came from their current system. So that's what their current system could do. They also wanted something that was lightweight and portable, which was not their current system, but they wanted something that they could move between sites. Because at that point, they were considering setting up sites at the Staples Center, which is a basketball and arena in LA. And perhaps also to LA County Hospital. So they wanted something they could easily carry between places. They also wanted something that was inexpensive because they were anticipating needing to make many of them. And then they wanted the system to be able to achieve 3 log reduction in growth. And that is actually the FDA standard. So that isn't necessarily their desire. That is, they wanted to be in compliance with the FDA. So that's reasonable. So we developed a system, we just brute forced it. And our first system was very simple. It was a UVC light bulb mounted on the side of a plastic bin. And this is actually a picture of our first system. Keep in mind this system didn't work, but I want to show it anyway. So it's very simple. So this UVC bulb you can get from a commercial vendor. The mount you get from a commercial vendor. The plastic bin we got at a store in the US called Lowe's. And the positive side of this is that it was very lightweight, very easy to make. You could plug it into a normal wall outlet. The downside is that the inside of the black bin is very absorbing. So while we had a very high UVC intensity on one side, the uniformity of the UVC throughout the bin was very low. So that meant we needed to create an optical cavity, right, to reflect and try to create a much more uniform light throughout the box or the tub. So we looked up the reflectivities of all of the different possible metals that we could add, and aluminum actually has the highest reflectivity of all the metals in 260 nanometers, which is UVC wavelength. Turns out that chrome spray paint is actually comprised mainly of aluminum. So therefore we could just take chrome spray paint, which you can buy very inexpensively at most retailers, and spray paint the inside of this bin, and we could end up with much more uniform light inside. At the same time, increase the optical field intensity inside the bin and not really increase the cost or any of the other metrics. And again, they were very easy to manufacture, if you want to call that manufacturing, because it was drilling like 2 holes in the side of a bin. So we did some modeling just to make sure that we were actually modeling and doing real science. So when we had 0% reflectivity, in other words, that original design, we weren't able to even theoretically achieve 100 millijoules per centimeter squared. And as you can see, also the power from our light bulb to across our bin decreased very quickly. If we assumed 25% reflectivity off of our chrome coating, we were able to achieve 100% everywhere inside of our bin, but it was still very non-uniform. And if we assumed 85%, then we were well above 100 millijoules per centimeter squared. And theoretically, aluminum has 90% reflectivity. So more than likely with our experiments, we're probably somewhere in between this 25 to 85%. I would guess 60% just conservatively. And that also would take into account things like scratches and, you know, just degradation of the coating over time. And these calculations assume, a 1 minute exposure time. So not 2 hours or something. So just some thresholds for comparison. So we used a 15-watt bulb in this work. 15-watt bulbs are a standard T8 UVC bulb that you can buy from at least a vendor in the US called McMaster-Carr. So they're very readily available. We didn't have to get them from a specialty healthcare vendor. And assuming only 1 minute of exposure, we're able to easily be above our, requested threshold. If you use a 10-watt bulb, obviously you're going to need to expose a little longer versus an 18-watt bulb. But either way, you aren't going to have to put your material in there for an excessive period of time. And just a few bacteria for comparison in terms of what their actual threshold values are. So if you look at anthrax and E. coli, which are 2 very well-known bacteria, they're both well below that 100 millijoule per centimeter square number. If you go to like norovirus, it's also well below that 100 value. If you go to an adenovirus, it's right at that 100 value. So that I think that the adenovirus is actually how the FDA chose that number and set it as a benchmark. So for our test system, we were designing our system around face shields. However, this was March and we didn't necessarily want to take a face shield and cut it into a bunch of pieces. That didn't seem like a good idea. So instead we used plastic petri dishes as a mimic. As our test organism, we used Bacillus cereus. We chose that because it's a gram-positive endospore forming, which means when you take it and put it on a plastic surface, it forms little protective endospores, so it's actually harder to kill. And it's UV resistant, which means it's going to be very hardy and hard to kill when you expose it to UVC. So basically, it's setting a really high bar for us. So we used that system. We verified that we actually had B series using MALDI to make sure that we didn't have something else in our system. We then plated it on sterile petri dishes and we performed a whole suite of studies. So we first did no exposure. We did different exposure times, so 1 minute, 3 minute, and 6 minutes of exposure. And we also looked at different locations within the box. So all of our samples were along the very bottom of the box. One of them was in the middle of the box, but at the bottom, and the other two were at the edges. So part of the reason we looked at the center and at the edges is because those were going to be basically the weakest, like worst scenario cases. So we didn't want to put it like right next to the bulb because that's kind of cheating. We wanted to make it as hard for us as possible because healthcare workers' lives, are at risk here. Then after exposure, we transferred it from that plastic Petri dish to a Petri dish with agar. We put it in an incubator, let it grow for 24 hours overnight. We also did an additional control where we took our bacteria and plated it directly on agar just to make sure that our bacteria was actually alive and happy. Then we counted the colony forming units manually. Yay. Luckily, seeing as we had many plates, doing the colony counting was really easy because the majority of the plates didn't have anything. As we were doing the plating and like putting all of these stacks into the incubators, I was feeling very stressed because I was imagining going into the lab the next day and having to count like hundreds of plates. And as we were looking, it was really easy. It was the best day ever. So when we had absolutely no treatment, we had millions of colony forming units. And those were the painful plates to count. When we had 1 minute, 3 minutes, or 6 minutes of exposure, when the sample was in the center of the box, we had absolutely no growth. When we had the samples at the edges, whether we had 1 minute or 6 minutes, in some of the samples, we had a little bit of growth, and that variation could have been because either I wasn't perfectly precise, and maybe some of the 6 minutes they were slightly in a different position, but either way, didn't really matter where we put it. We always got 3 log reduction in growth, which was our metric. So we always hit it. So when we told the LA County and USC Hospital what the protocol was, we told them 3 minutes because that was very safe margin. So there's always been this lingering question about if UVC will impact filtration efficiency of N95 masks, because a lot of researchers have looked at the intensity of UVC you need in order to actually inhibit bacterial growth and viral growth, but doing a filtration efficiency test is actually really challenging because there aren't that many filtration efficiency measurement systems. And we're really fortunate because at Caltech, there actually is one of these systems. So we took our UVC exposure system and did a series of measurement systems with KN95 masks. So how this filtration system works is you have an air blower that inputs particles of a known size into a chamber. You have a head model, and you actually mount the mask onto the head model, and you put a wax seal around your mask so that you get a really tight seal around the mask. So you don't have to worry about doing a fit check. You then have a hose that basically pulls particles through to try to get the maximum number of theoretical particles through. And then you have a particle counter. So it measures how many particles you're actually able to pull through the mask. In our experiments, we had a flow rate of about 22 liters per minute, and we were looking for particles above 300 nanometers. We did 2 types of measurements. So the first type of measurements, we actually did iterative exposures. So we did 3-minute exposures and then would measure the filtration efficiency, then did another 3-minute exposures, then measured again. And we did this 40 times. So this is effectively looking at cycling masks 40 times. Then using that same set of masks, we did 2 long exposures. So 2 overnight exposures, continuous UVC exposures. And you'll see why we stopped doing the cycling. So this is a subset of those 3-minute exposures because the graph got really and we did this on 2 masks. So the error is from the 2 masks. So basically, we didn't see any change because this is 99% filtration efficiency. So we didn't see any change in the mask filtration efficiency over the course of the cycling. And then because there wasn't any change, the PhD student got tired of doing the cycling and decided to just put it in the box overnight and see if he could get any kind of degradation. And after the first overnight exposure, he didn't see any change. And after the second overnight exposure, he didn't see any change. And so then he decided to stop doing the experiment because he's like, I don't know how long I would need to put it in there, and I'm tired. And we also figured that basically at this point, because this would correspond to several hundred cycles, probably whoever was using that KN95 mask is going to stop wearing it because there's going to be other problems with it. It'll get gross. So that was a pretty robust experiment showing that, you know, UVC isn't going to damage the masks. So in the future, where we're planning on going with this work is expanding applications of UVC. So not just looking at using it as a way of cleaning masks or cleaning face shields, but actually integrating it with semi-autonomous systems. And I know there's a lot of work going on. For example, there's a startup company in Sweden looking at integrating robotics and UVC systems. There's a professor at USC, S.K. Gupta, who does a lot with semi-autonomous systems. So we're looking at integrating a UVC light source with a handheld wand to try to automate this type of system. One of the advantage of having a robotic system as opposed to the freestanding vertical UVC source is that you would be able to manipulate things on surfaces and improve the exposure. Additionally, we're looking at developing ways to integrate UVC exposure into existing systems, like for example, X-ray screening at airports. So as your luggage or backpacks went through an X-ray screener, it could also go through a UVC screener, so that you could do preventative type measurements. And then there's also just not us, but other people. There's a really cool new ATM keypad screener that came out by GenMega. So you can use an ATM, and then after one person uses it, automatically cleans the keypad. So that was announced like a month ago. While that's great for ATMs, I'm really hoping to see something like that on like elevator doors, things like that. I think that's much better application. But they make ATM machines. So okay, so moving on. So we're gonna move on to portable diagnostics. Again, first talk about tissue and then malaria. So the first step in a diagnostic design is to pick a biomarker. So basically pick what you actually want to detect. And that's going to depend on if you want to detect something at the molecular level, at the cellular level, at the tissue level. So molecular level, you're talking about things like genetic variations or antibodies, and it could be an antibody in response to something that's in the blood. It could be an antibody on the surface of a cell. And at the cellular level, you could be looking for non-native cells, so perhaps the cell that's actually invasive, or you could look for changes in cellular morphology that could be indicative of a disease. And at the tissue level, you might be monitoring more for activity. So you could be looking for changes in neural activity indicative of a disease. You could also be looking for the presence of abnormal structures. So for example, the presence of a tumor. So changes in your tissue structure. So the second step is determining how you actually want to do this detection. And one of the oldest ways of doing detection is palpating. So basically trying to feel that change. And the idea of palpation has been around for, thousands of years. It was one of the most obvious ways you feel a lump. Ancient Greece, ancient China, it's been around for a while. And mechanical behavior is a very good indicator of disease, which is why it was one of the original approaches developed. Obviously, palpation isn't necessarily going to detect osteoporosis, but it's a great way of detecting cancer. So when you're trying to detect mechanical disease or mechanical behavior, we've now kind of advanced beyond just using our fingertips. And we now have a lot of quantitative approaches, ranging from AFM to load frames to sonoelastography to OCE. And there are advantages and disadvantages to all of these different approaches. So the nice thing about sonoelastography and OCE is you actually get a picture. So you can actually see the mechanical behavior in the greater context of the human body. The disadvantage is related to both the penetration depth or the resolution. So, being able to actually see deep into the body. Whereas AFM, you get really, really high resolution, but you can't do AFM in your body. We aren't there yet. And the load frame is probably the oldest method for characterizing mechanical behavior. The advantage is that it's non-destructive, but you have to resect the tissue. Additionally, the resolution of the load frame is limited to the sensor chip or sensor array. And I use that term incorrectly because there isn't a sensor array. It is a single sensor pad. So, Professor Fun was talking about how, he had 100 electrodes on a chip. This is the equivalent of having one. So the ability to improve it is gigantic. If you go to 2, suddenly you've improved it. So that was our goal, was to take the load frame and simply improve that sensor array. So our approach was to use optics. So instead of having a single sensor plate, we wanted to create a sensor array so that we could detect the heterogeneity of tissue across a sample of tissue. And while we can use that conventional load frame to apply compression, we wanted to have something portable and smaller. So we're using the same philosophy of a load frame that applies a vertical pressure, both to, compress and relax tissue, and that we can do repeatedly, but we basically built a custom load frame. So it had a micrometer stage that was motorized, could apply vertical force very consistently, but it was on, a breadboard with a, micrometer stage with a, motorized system, because load frames are heavy, whereas our system wasn't. So therefore we could carry it into the hospital and carry it out again. And it was very fast to set up. So our sensor array works on something called the photoelastic effect. So the photoelastic effect basically says that as you apply pressure on a material, the refractive index will change due to the stress in the material. Now, if you're just looking at a change in refractive index in a waveguide, in a material that transmits light, that refractive index change is going to be pretty small. However, if you're using a material like a polarization maintaining optical fiber, you can actually detect a change in polarization. So monitoring a change in polarization of an optical field as opposed to a change in optical power is a much more sensitive measurement. So changes in optical power are very sensitive to things like fluctuation in your laser power, fluctuations in temperature, just fluctuations in vibration, whereas changes in polarization are insensitive to all of those variables. So you get a much more robust measurement, especially when you don't have access to things like vibration tables. So you're doing measurements, in a surgical ward. So that's why we decided to do polarization maintaining polarimetry as opposed to just polarimetry. So these are example measurements on pancreatic tissue. So on the left shows the signal being generated by the micrometer by a function generator. So the micrometer moving up and down to compress and relax the tissue. The blue is the signal measured by the polarimeter. so the power going through the polarization maintaining optical fiber. If you notice, they track each other, but they aren't perfect. And the reason is because the response generated by the tissue is something called viscoelastic. So when you take the signal here, and then you convert it to a change in polarization as a function of strain, or this y-axis, you can see very clearly the viscoelastic curve as the material is compressed and then relaxes. And the fact that there's a little tiny gap here just indicates that a little bit of energy is lost in this measurement because we overcompressed it a little bit. So it's an indication of measurement error on our part. So we did this measurement on many different tissues. These are just 4. So liver, kidney, pancreas, and heart. It's important to note that all of the tissues were measured within 2 hours of resection from the animal. So if you wait too long to do measurements from time of resection, then the mechanical behaviors actually change significantly. So you need to do measurements fairly quickly after resection. And on one hand, this makes sense intuitively because obviously tissue begins to degrade due to enzymatic reactions that happen in the tissue. On the other hand, a lot of measurements on the biomechanical behavior of tissue are done on cadaver tissue or on dead tissue. So even though this seems somewhat intuitive, it's sometimes not actually put in practice. So as you move across these 4 tissue types, the Young's modulus, which is a classic metric used to characterize the elasticity of tissue, increases. Additionally, you begin to see very different behaviors. So while both liver and kidney are fairly elastic, the pancreas and heart, as you have higher strain rates, they begin to have this slight buckling behavior. So this slight kind of bend over is indicative of buckling in the pancreas and in the heart. And this kind of loop that actually happens in the heart has to do with the alignment of the cells in the heart because it's a muscle. So this buckling behavior we're going to talk about a little more in the context of cartilage. So cartilage is a particularly unique tissue. So when you look at cartilage in the knee, there's actually 3 distinct types of cartilage, which I've color-coded here. So this is a schematic of a knee. So the 3 types of cartilage, even though they're all called cartilage, they all have slightly different structures because they all play different roles. So the first is articular cartilage femoral condyles, which is weight-bearing. And it's basically designed to try to glide as you put weight on it and as you move your knee. The second is articular cartilage patella. And this is designed to basically be a shock absorber. So as you run, it will help absorb shock. And it's also one of the thickest cartilages in your body. And then the third is fibrocartilage meniscus, and this is also a shock absorber. And it also helps if you decide to carry a lot of weight and then do something like run. So it's also plays a very important role in basically helping your knee maintain integrity. So when we analyzed the different mechanical behavior, it wasn't surprising that we saw very different mechanical responses to loads, to force being applied. We also saw significantly different responses in general. And note these are 5 different runs on the same sample that were applied sequentially. So they aren't our 5 favorite runs or something like that. They're just 5 runs that we did right after each other. So for example, the fact that this series of runs were beginning to kind of degrade is actually, has some information in it because there's actually a trend there. So we can go through and look at all of these data sets and try to deconvolve the different behaviors that are occurring in these much more complex mechanical behaviors. So given that cartilage has a type of structure, we can consider the different types of behaviors we might see. So the first is buckling. So buckling describes that if you have a series of laminar cells that are all perfectly aligned and you apply a force, after you compress it, your perfectly aligned vertical cells will begin to buckle, or they'll become squished. And on a stress strain curve, this type of behavior will look like little bumps in your stress strain curve, and you can have, primary bump or secondary bump, and then as you relax it back, you will again, have the recovery of your buckling. The second type of behavior you can see is delamination. In delamination, your cells will be vertically aligned, and then as they separate or delaminate from each other, they can either delaminate, both in different directions, or you can only have a single sheet that separates. And unlike buckling, where it will go up, if it separates from each other, it will go down. And bridging describes when, as you apply pressure, you actually end up with networking in your cartilage. When this happens, your cartilage actually becomes stiffer. And so this is shown with a quick increase, but then a subsequent decrease. And it's a very sharp increase and then decrease. Both of these second two are considered basically your cartilage degrading over time, so becoming worse in behavior. And they're actually signs that we're either applying too much force and operating outside of a normal physiological condition, whereas buckling, because if you see it recovers, that is a normal healthy cartilage behavior. So if we look at specifically focusing on buckling behavior and identifying the buckling points in our data, so for that primary loading buckling point, or this buckling point, all three of our cartilage types over all three strain rates that we applied showed that primary buckling point, which is good because you want cartilage to absorb shock, and the primary way that they absorb shock is by buckling because it can recover. At 30% strain, two of them also exhibited a secondary point. However, we should note that 30% strain is actually like on the verge of being outside of a physiologically relevant strain. So that might correspond to, if I, as a very small person, carried a 200-pound backpack and then ran down a mountain, that would be that 30% strain. So that's not really something that would normally happen. So then the unloading buckling, again, all three cartilages absorbed or exhibited that, unloading buckling. Additionally, what's really important to notice is that over those 5 measurements, it was consistent. So we didn't see a degradation in either the loading or the unloading buckling, which might indicate that it was degrading over time. And even this really high secondary loading buckling also didn't degrade over time, even though we were operating right at the relevant, non-relevant strain. So on my last topic, because we started a little early, Paul, we're going to talk about malaria. So malaria really is a 2-step cycle. So the first part of the cycle is when a host mosquito bites a human and transfers the parasite to a human, and then the human acts as a host and either becomes symptomatic or asymptomatic, and then a mosquito again, specifically in Aedes aegypti, mosquito again bites the human, and then it goes into the mosquito, and then the mosquito again acts as a host for a little while, and then eventually bites the next human. Which means when you think about trying to combat malaria, there are 2 strategies. You can either try to combat it in the mosquito, or you can try to combat it in the human. There's been a lot of work on both strategies. So trying to combat in the mosquito, some of the common approaches are doing genetic engineering of mosquitoes, specifically to try to make the mosquitoes that can act as hosts not functional and just eliminate that type of mosquito. Also using pesticides, using pesticide-treated nets. So those are some of the most popular strategies. Then in the human, developing new types of therapeutics, developing more efficient diagnostics. So there are lots of approaches, but there's kind of two themes. Just to give an idea of kind of where malaria is most prominent, as well as the type of malaria that's most prominent. So there are 5 strains, but really 2 strains are the most prevalent. So P. falciparum and P. vivax. They account for 95%. However, when you're thinking about trying to combat it in the mosquito, the majority of P. falciparum is pesticide resistant, which means going with the pesticide approach is not effective. And the idea of continuing to do pesticide is just going to make more pesticide resistant malaria or more pesticide resistant mosquitoes. So that's not an effective strategy, which is why the idea of genetic engineering mosquitoes is really strong. Additionally, malaria is one of the leading causes of morbidity and mortality. And this is a very important point. The infected population consists of 2 distinct groups, symptomatic and asymptomatic carriers, which is a point that we're all very familiar with right now, the asymptomatic and symptomatic carriers. Specifically, no disease is ever going to be cured until the asymptomatic carriers are identified. So when you think about a healthcare treatment workflow, the first step in that healthcare treatment workflow is the patient being aware that they have symptoms and seeking care. Right? Like that's a key component. Then, you have the intermediate, which is coming up with an accurate clinical diagnostic, doing diagnostic testing and staging, and then referring for treatment, and then actually getting access to treatment. So those are kind of the 3 big picture steps in eradicating any type of disease. So there are 2 categories of diagnostics. Diagnostic screens. So screens allow for broad decision making, and this can be, you can think of this in terms of like, do you have the flu or bacterial infection? Not necessarily trying to determine what type of bacterial infection you have, what type of antibiotic you should get, but should you go for more detailed bacterial diagnosis, or do you have the flu and therefore antibiotics shouldn't even be considered anymore? Diagnostic tests allow for precise disease identification. Do you have MRSA or SA? Do you have an antibiotic resistant bacterial infection, or do you have a bacterial infection that can be treated with a normal antibiotic? The reason why screens are a super critical part of this entire workflow is if you have an effective and inexpensive screen, you can just screen an entire population, right? You could just go into a city and screen everybody and therefore identify that asymptomatic group that may not even go and like try to assess care or access care, and therefore they would never be evaluated and they would never try to get treatment. So inexpensive screens play a critical role in trying to eradicate disease. So currently there are 2 main types of diagnostics. The first is the rapid diagnostic test, and the second is imaging. So the rapid diagnostic test is the more modern of the 2 types of malaria tests. It's an antibody-based test, and there's actually 2 antibodies on there. So the first is specific to P. falciparum, which means that it will detect 75% approximately of malaria cases. And the second is a pan-malaria antigen, which means it will detect all of the malaria species. So it's just kind of a global test. So it's very user-friendly. It's basically like a stripe test. It will give you very quick results. The downside is that it is an antibody-based test, which means you need to be very careful about the storage conditions. Otherwise, it will stop working. And for that reason, a lot of times the general rule of thumb is that if you get a positive, you have malaria. If you get a negative, you might still have malaria. So it's very hard to have a lot of faith in the RDTs. So the imaging is kind of the gold standard for malaria. It was the original malaria diagnostic. You basically take a blood sample, smear your blood across a cover slide, put it under a microscope, look for the ring that forms around or within the red blood cell. That's indicative of the parasite digesting the hemoglobin. However, it requires somebody to actually go through and count red blood cells that have rings, which means that, if you're at at a national lab in, China, in the US, you're a, PhD trained scientist, you're going to do a really good job counting. If you're trying to run through 10,000 tests, you might miss a lot, simply because it's very time and labor intensive. And for this reason, both of them have problems detecting very low levels of parasitemia. And the reason why that is important is because most therapeutics are incredibly effective early on, but they're not super effective after the disease has progressed. So having a diagnostic test that's very effective after a disease has progressed is really important. Additionally, malaria, because it is a parasite, it can come back. So the parasite can actually hide out in your liver and then recur, which is one of the scariest things I've ever heard when I learned that the parasite could just hang out in my liver. So we wanted to look for an alternative biomarker. So again, the ring formation around your in your red blood cell starts around 12 to 18 hours. Antibody production also begins around 12 to 18 hours after the haploid is released from your liver. Hemozoin production begins around 18 to 24 hours. So it's a little bit later. On the other hand, for every ring formation, you get multiple hemozoins. So it basically amplifies your signal. So you get more of them, even though it starts a little bit later. So it could be a little bit easier to detect. So the question really is, what is hemozoin and how is it produced? So hemozoin is a biomarker for the parasite because it's actually generated when the parasite digests your red blood cells. So how it works, so the parasite first remains in the liver reproducing until there's enough of it that it's actually released into the bloodstream. Then as the parasite begins to digest your red blood cells, heme is generated as a byproduct of the hemoglobin digestion. However, heme is actually toxic to the parasite. So the parasite basically sequesters it in vacuoles, and the process of this sequestration and the heme agglomeration turns heme into hemozoin. And then eventually the parasite leaves your red blood cell and the hemozoin is released into circulation. So you end up with these hemozoin crystals. Hemozoin has a lot of really amazing properties when you're thinking about trying to develop a diagnostic around it. So first off, unlike all other naturally occurring materials in the blood, it's paramagnetic. One common question I get is, if we don't have any paramagnetic materials or any magnetic materials in our blood, how does an MRI work? This is actually quite simple. So an MRI uses a really, really, really high intensity magnet, first of all, and it's actually detecting switching, whereas the hemozoin is a very large nanoparticle, and you can actually detect it with like a kitchen magnet. So it's a totally different level of magnetism and type of magnetism. Not MRI-esque magnetism. So it's also opaque and birefringent. It's elongated, so it's between 200 nanometers to a micron long. And there has been an artificial type of hemozoin developed by some very clever chemists. And the artificial hemozoin is called beta hemotin. and it shares all the same properties as hemozoin. So the same unit crystal structure, the same optical properties, the same magnetic properties. So everything is the same. Additionally, so the reason for this length range, because obviously 200 nanometers to 1 micron is fairly large, all of the different species of malaria produce hemozoin. The difference has to do with the length of the hemozoin that's produced. So we did not discover hemozoin. It was actually discovered in like 1880, although they didn't have TEMs, so they didn't actually know what it was, but they discovered it. And since then, there have been several groups that developed hemozoin-based diagnostics, two that are commonly referred to. So one of them actually leverages flow cytometry. So it's a polarization-based measurement. And the second leverages birefringence imaging as well as polarization detection. Both of them get very, very, very high sensitivity. So the magneto-optic method can actually detect individual hemozoin particles, which is amazing in terms of sensitivity. However, that level of sensitivity isn't really needed in order to diagnose malaria. So when we started trying to develop a system, we really wanted to prioritize things like the operating cost, the maintenance cost, something called SWAP, which describes the size, weight, and power needs, as well as the operation environment. So, where is this going to be operated? Is it going to be operated in, a healthcare center? Is it going to be operated in the field? So what kind of consideration should we include in our design? And we wanted to design for that, as opposed to design something and then have to try to adapt it. So one immediate thing that came to mind, given that it's opaque, was optical spectroscopy. And optical spectroscopy is really old field. It's been used for a very long time. A brief background on spectroscopy. If you have a solvent or a solution you're trying to measure, and you put in a whole spectrum of light, if the solvent is absorbing, a lower amount of light will come out the other side. You can quantify the absorbance of your solution using this very nice law, which is also called the Beer-Lambert law. And then you can determine all sorts of properties of your solution. One of the key points is that your solution needs to be consistent. Time evolving solutions mean you need to take measurements over time. You can do that. So there are lots of examples of how this is used in science. So one example is to analyze surface plasmon resonances of particles. Another is to look at reaction rates and kinetics of experiments by taking multiple measurements of time of your solution. However, part of the challenge with trying to apply this directly to healthcare is that blood, which is what we want to analyze, is significantly more complex than a nice solution with a nice single dye molecule in it. So blood consists of plasma, which has water, blood proteins, nutrients, hormones, electrolytes, waste stuffs, as well as red blood cells, white blood cells, platelets. So then you have this combination of things that are going to absorb and a combination of things that are going to scatter light. So it becomes a significantly more complex analysis. Additionally, you can't establish what healthy is. And part of the reason why establishing healthy is so challenging is because even if you take my blood and you measure it like 6 times during the day, you're going to get different answers. And the reason is because oxygenated blood and deoxygenated blood are very different, because the oxygen changes, in the presence of oxygen, changes the UV vis spectra that you'll get. So this means that we need to think about what is an alternative strategy that we can use to use UV vis as a way to measure the absorption of blood, and take that background out that has to do with my personal variation due to how much water I've drank, or due to if I went running, or what altitude I'm at. So we decided to do something called differential spectroscopy, which basically means we're taking 2 measurements. One where we take a measurement that's just how much is my blood absorbing, and one where we put a magnet close to the sample, which would then remove all of that hemozoin and take a second measurement. And if there's hemozoin in the blood, then we would actually expect to see a change in the measurement. And if there isn't any hemozoin, then the measurement shouldn't change at all. And this normalization process basically removes any kind of background or variation due to me as a person, because we're just monitoring a change in transmission. And we do this at a single wavelength, so we don't have to take that entire spectrum. We're just monitoring how much power makes it through at one point. So our first device, and for all the students out there, this is why you should always take measurements and images all the time. Because this is the first device that my student made ever as like a proof of concept measurement. And I went into the lab and she showed it to me and I took a picture and she was like, "Why'd you take a picture? This is horrible looking." And I was like, "Yes, but it's memories, right?" Like it was a landmark measurement in this whole project. So this was the first device we constructed, which by the way, a high school student helped with. And as you can see, it makes very little sense and doesn't look like the very nice schematic I drew on the previous slide. But it worked. We were able to get a signal and we were able to show that the concept worked. Because I told her if she got a signal using spare parts we had in the lab, then I would actually give her money to buy things. And she got a measurement with spare parts. Including, in order to align the cuvette with our laser source, she put it on plastic boxes to get it to the right height. So, brute force engineering. So while she was able to actually get a signal, so the light source or the laser comes through the cuvette, is detected with this detector. That red thing on the back is the magnet. So she basically pivoted the magnet in and out. The sample holder, which are these plastic boxes, wiggled a little bit. But basically all of the metrics we established of initial and operating costs, maintenance, size, weight, and power, as well as ruggedness, none of those were met. So everything was off. So we needed to address all of those. So 6 variants later, sometimes I show them all, sometimes I don't. We have pictures. So 6 variants later, we had a system that looked like this. So this was all battery powered. It was controlled with a laptop. However, this 10-inch by 12-inch bottom piece was actually a steel breadboard. It was portable, but it was steel, so it weighed a lot. This sample holder was actually on a pivot plate, so we could take multiple measurements without actually opening our system, so we could validate what our measurement was multiple times. Our magnet was on a pivot, so we were able to switch the magnet on and off without actually having to do anything. So it we were at the rugged part kind of, but we definitely hit the maintenance and initial operating costs, things like that, pretty well. But we weren't 100% there yet because the weight was still super heavy. So our final design, we basically replaced everything with 3D printable parts. The only thing that we hadn't fixed yet really has to do with the sample volume, which right now we're at 500 microliters, but we have a solution for that too. But that's kind of the last thing that we're working on. So we did a lot of trials, first looking at spherical iron oxide nanoparticles with the first 5 iterations. Then we went to the 5th iteration. We also looked at beta hemotin, which we synthesized, and then we looked at beta hemotin doped rabbit blood. And then right now with the 7th iteration, we're looking at actual hemozoin generated by macaque monkeys. So the validation in rabbit blood. So these are a set of the different sample numbers, which are shown up here, the concentrations, which range from 0 micrograms per milliliter to 3 micrograms per milliliter, as well, the black line is a control. Over, fairly short time span, and the change in power. And this is in milliwatts. So it's, about 6 microwatts. So our detector sensitivity that we have in there is in the picowatt range. So microwatt range is well within the noise. The shaded area is actually a theory that we developed based on a combination of mass transport and electromagnetic scattering and the absorption of the nanoparticles that we measured. So the error basically takes into account all of those different variables. So the size of the nanoparticles we measured using TEM. The sample protocol, we started with whole rabbit blood that we treated with ultrasound. So we treated with ultrasound to lyse the red blood cells and white blood cells. If we didn't lyse them, then we basically just got a lot of scattering off of them, and we didn't really get any kind of signal at all. Then we added beta hemotin at known concentrations. And then the test was actually done with 5 to 7 drops approximately of these different solutions. We then looked at the reproducibility in those results. And the one thing that was interesting was at the relatively high concentrations, we saw a lot of noise, and we think that's because the beta hemotin began to start fluctuating and clumping. And then we took the concentration down really, really low. And if you plot this on a log scale, you can see that we're kind of right approaching that limit of detection. However, that corresponds to about 26 parasites per milliliter. And if we do 3 measurements in a row, they all tightly cluster. So the remaining challenge is actually reducing that sample size from 500 microliters to 200 microliters. And an obvious question is why? Right? Like, why do you need 200 microliters? That seems like a magic number I'm just pulling from somewhere. And the reason is actually pretty simple. So 200 microliters corresponds to about 1 to 2 drops of blood, whereas 500 is 5 to 7 drops of blood, and you usually can't get 5 to 7 drops of blood from a finger prick. And 1 to 2 drops of blood you can get from a finger prick. And the difference in complexity in terms of getting that sample is significant when you start thinking about biological waste. So a finger prick can be a single needle, and the bio waste is just the finger prick bio waste. Whereas if you start needing 5 to 7 drops of blood, that's going to require a syringe. And a lot of people are really afraid of syringes. And so that's going to be a mental and social hurdle. Plus, you're going to need a trained nurse to actually do that syringe draw. And the sample preparation complexity is going to be a lot harder. If you can prepare that small needle for a finger prick, then you can start designing our sample holder around that finger prick design. So we're making progress. Our new system actually looks like this. So we completely redesigned it. So our sample holder is actually buried in here. The entire thing is battery powered, and the battery is actually embedded inside. The whole thing is Raspberry Pi controlled. And we have a 4 keypad thing on top, and you just hit on off. And then the readout on what the signal is happens on this little tiny display screen. So when Paul was asking what my high school student's working on this summer, he's working on part of this system. So he's super excited because the whole point of this is that it can be portable and do at home and things like that. So we're really testing it out. Is it portable and can you do it at home? But he's working on dyes, not blood. Okay, so in conclusion, we're looking at UVC disinfection. We showed that we can design and construct a UVC disinfection system. We validated 3-log reduction in growth. And we verified that we had negligible impact on KN95 filtration efficiency. And then in the portable diagnostic realm, we designed and constructed an optical elastography system, validated the system with a range of organ tissues, covering several orders of magnitude of Young's modulus. And then we also designed and constructed a malaria diagnostic, and we're working on achieving lower sample volume requirements. And again, I want to thank all my group members and thank everyone who is still with me. So thank you, Paul. I'm happy to take any questions.
Thank you so much. Let me bring up the screen here. And there we go. So we have not only quite a few questions, our audience has grown to over 390,000 people. So
welcome.
Yes, thank you all so much for being with us. Let's move on to the first question. It's very wonderful, Professor Armani. I want to ask you, this is really back to the panel.
Yeah, great.
How you select the high school students in your lab and how long do they normally stay?
So I select the high school students on a two-step process. I accept nominations from high school teachers, self-nominations by high school students, and the nomination consists of basically a CV, so a resume or curriculum vitae from the high school student, which again is a high school student. So I'm really more looking for just what they've done. I really like students who've participated on teams because it shows that they can work well with others in really any type of team, sports, chess, anything. And then I ask for like a 200-word statement on why they want to do research or like what is their personal motivation. Because doing research requires a time commitment. So I want to make sure that they have a goal, right? Like they have an end goal. That's really all I ask. And then once I down select, I'll interview between 5 to 10 students and I interview them, and then the PhD students or postdocs who are planning on mentoring that summer will also interview. And depending on how those interviews go, I may take more than one. I want to take at least one every summer, but some summers I've taken 5 because if, 5 of my PhD students all really lobby for their high school student that they really want, then, it's my PhD students who are really committing to this. So,
fantastic.
So it's a two-step process.
The next question, can this UVC scanner be cheaper, faster, and safer, and perhaps used in airports and train stations?
The system we developed, I really designed it to be used almost as like a personal system, right? So a lot of my friends, a lot of my PhD students have built one for their groceries and their mail, and they have it right at their front door in collaboration with SMP Engineering. So they're a local business. They built 55 of them for the LA area and donated them to hospitals and small clinics in LA. So that was kind of our goal. I know that there are a lot of companies building UVC scanner type systems for airports and train stations, as well as hotels. And I think another company is working on building one for schools. Personally, I don't want to have a startup company. Whenever someone emails me and asks for advice, I'm happy to give advice, but I don't want to have a company. I'm happy to give advice to anyone. I view right now as a pandemic and we should all work together. I don't necessarily want to make a profit over people's illnesses. So.
Third question, Professor Armani, spectacular talk. For the mechanics of cartilage, can it be tested in vivo? As there are many others and runners, cartilage damage through this problem.
So we're actually working on an in vivo system. So this is a great question. I get asked it a lot. So we're working on an in vivo system where we're going to pattern basically gratings on the end of optical fibers, leveraging a lot of existing technology for doing e-beam patterning and making Fabry-Perot type structures on the end of fibers that we could then insert with needles. And I agree. I'm a runner. I'm well aware of the problems. I have a personal motivation for doing this. Yes, so I know. But yes, we're looking into this. Yeah.
And actually, I had a related question, and that is,
have you tried doing these compression studies using the shapes that would be in either healthy or damaged knees? I remember working with our orthopedic surgeons. They had human cadavers, and they would try to come up with a way to measure the pressure points within the cartilage on using a robot, but they didn't have a good readout. But it seems like you would have a system for solving that problem.
Yeah, so we're doing something similar but a little different. So we're using our system with cartilage. So we're doing two similar measurements. So the first is we're using our system with porcine cartilage. So actually, pig knees and human knees have almost identical structure, and we're yeah, which was I didn't know. So we're starting off with healthy cartilage, and then we're measuring and analyzing that, and then we're damaging it to see what frequency of damage, forces, intensity, duration, so various types of force applications. And then the second is we're working with an orthopedic surgeon, and we're have the IRB in process right now. So we will be, I'll put it that way, working with an orthopedic surgeon, and he's going to be giving us samples. So he focuses on shoulder and knees. So we'll be getting shoulders and knees. And looking at the difference in degradation between shoulder and knee replacements for elderly versus young patients. Because both categories of people get replacements, but the damage is very different, and the types of damage, right? One is more catastrophic versus one is more just use. So we're looking at both. Again, I've had both ankle reconstructions and shoulder reconstructions, so we're working with my orthopedic surgeon, which right. I mean, if you ever want a really good collaborator, it's very effective. Yeah.
Yes. We great. Often find that our doctor's appointments turn into collaborations.
Yes. Yeah. So.
And our next question is, thank you for the inspiring talk. You mentioned that Hemozoin can be used as a biomarker for malaria. Are there interesting biomarkers in sweat or saliva that can be used for wearable detection? And do you have insight into other diseases that also might have biomarkers in sweat?
So to my knowledge, and keep in mind I could be wrong, I don't have any insight into other biomarkers in sweat or saliva for malaria detection. That said, I know that there is some research being done on detecting hemozoin through the skin, right? Because it is circulating, it is magnetic. So there is some research on looking at detecting that magnetic signature through the skin in areas where your skin is very thin. So that is an area. So other diseases that might have biomarkers in sweat, I know that there are several diseases that have biomarkers that you can sweat out. I also know that just the idea of monitoring changes in your baseline physiology, right? So if you start getting, if you start having like very low hydration levels, which could be indicated with changes in salt content in your sweat. So markers like that can also be indicative of disease, even if it can't necessarily be indicative of a specific disease. It can just be indicative of a change in wellness, right? And that's becoming a increasing area, is just monitoring your level of wellness so that you can take preventative care. So if you start becoming less hydrated, that can lead to disease, even if you don't already have a disease. So just taking better care of yourself is always a good idea.
And actually, I had a related question. Are there other magnetic biomarkers that one finds in blood, or is it the hemozoin so strong and prominent in these cases that one doesn't have to worry about anything else?
Yeah. So there are a few tropical diseases located in the Southern Caribbean that can generate similar magnetic biomarkers, but they aren't co-located strongly. They're rare tropical diseases. So for the most part, if you see a magnetic signature, it's going to be indicative of malaria. On the other hand, if you see a magnetic signature, it's going to be indicative of a disease. So you're going to want to get tested for things.
And our next question didn't quite make it to print, but we'll bring here. Once you can reduce the sample size to 1 or 2 drops of blood at the 200 microliter target that you had, what's the power consumption like in the device that you produce?
So right now, the power consumption in our system, we're using a USB connected battery. And the system we have right now can run for 16 hours continuously, which is very long. It's a rechargeable battery. So you can plug it into a wall and recharge it and then continue going again. Obviously, we've designed the system such that, as batteries get better, like that whole top part peels off. It's 2 parts. So you can just put in another battery and it's USB, so you can just USB connectorize it again. It's not hardwired in. So we intentionally tried to make it very modular so that if one component failed, the entire thing didn't have to be thrown away. We did this because personally I'm very frustrated with my laptop because the whole thing is sealed. And so if one thing fails, like my laptop is just gone. And so I didn't want to have a system like that. I wanted to have a system where, if the battery failed, like the top just pops off and you can replace the battery. If, a button failed, like everything you can just pop off and replace. So again, I tend to be very influenced by the environment around me.
Yes, it's both an inspiration and a guide, I think, in guiding your work. Well, that was just fantastic. And of course, if we were in person, which we miss being very much, we would have this certificate and plaque for you, thanking you for this talk. We can update the title with the one that you ultimately gave. That was amazing and inspirational. So thank you both for these wonderful talks today. As I mentioned, a few minutes ago, we passed by 390,000 in our audience, and we'll get a final number for you later. And I think we all want to thank Professor Alice Shang for amazing work in putting these talks together. And we just got the latest number, 400,023 attendees. So we crossed that milestone, I think, only for the 2nd time in the entire series. And congratulations to you both. Next week, we're going to have Professor Robert Shepard from Cornell University, which is from my hometown where I grew up, and Professor Philip Kim of Harvard University. And our host will be Mizo Kim, who was one of our ACS Nano Rising Star speakers earlier in the series. And the theme of the talk will be new materials and new structures. And speaking of the Rising Star lectures, our 2nd cohort of those will be held on September 4th with Yingying Zhang from Tsinghua, Zhang Liu from Nanyang Technological University in Singapore, and Shelley Claridge from Purdue University. So stay tuned for those as our cohort of amazing speakers grows. I'll remind you that you can watch all these talks. They're recorded. They're available on YouTube and other venues. You can go to the website here to find the ones that you can watch where you are, if you have VPN and YouTube's block. And also, these talks are available in Chinese transcriptions within a couple of days. So thank you to the students who've been doing those Chinese translations, and you can read along with the talks if you like. And with that, I will bring today's lectures to a close. Thank you all, and thank you again to our speakers and to Professor Alice Shang, who really has been connecting the world of science and engineering together with the ICANX talks. Thank you very much.
Thank you.